chemistry. We are now looking into starting to name and write chemical formulas, and we're going to start with ionic compounds. We will have another video on acids and another video on covalent compounds as well. So as I've been saying, this is a presentation that at least the PowerPoint itself was created by another very good chemistry teacher, but I am using it to kind of continue to go through the different topics that we got. So here we go. So writing ionic compounds. So last unit we talked all about what ionic compounds are. They're a metal and a non-metal. They're formed between a cation and an anion, and they are attracted because of that opposite charge. They form hard, hard solids, and just have a lot of different neat properties. So we are now really getting into how to write out the chemical formulas for these. We were kind of writing some of these in the last unit in terms of just at least showing them, but we didn't really get into detail of how we put them together and why they had the subscripts and everything that they did. So the two big things to kind of understand about writing ionic chemical formulas, and this is kind of true, we're going to kind of go through, I guess we'll say 3 variations of this. They're not really variations, they're just, you know, we have ones that might have just a slightly different rule. But this first rule is always true, is that the overall charge of the compound must be 0. So those positive cations must be canceled out by negative anions, okay? Which is why you might have more cations than anions if the charges are not the same, and therefore you might need an additional positive charge to cancel out the negative charge. We are using what's called the CDR method, which stands for cross, drop, and reduce. I will show you that. I'll also kind of use another method just to show how clearly why the CDR method does work in the end pretty much every time if done correctly, and we'll go from there with it. So, I mean, we jump straight into it, right? The chemical formula for potassium iodide, okay? So the way we should go through this, or I recommend going through it, okay, is we first need to make sure we know this is an ionic compound. I know we're only doing ionic, but pretty soon we're going to be having other types, and we're going to mix them all up. This is an ionic compound. A couple of signs of this is we have a metal and a non-metal. Potassium's on the left side of the periodic table, iodine's on the right side. I mean, that is really the best method of knowing it's an ionic compound. Another one that will come up, excuse me, is there are no prefixes. Okay, we will learn a different type of compound. We'll use prefixes to help you figure out how many atoms there are in the formula. And you don't see any prefixes in ionic compounds. Okay, so the approach. What I would really recommend doing first is using the name, figure out the charges of the 2 elements. Okay? And so potassium is an alkali metal and is in the first column, so it would have a charge of +1. Okay? So this is important. Okay? We got +1. Iodine, it says iodide. We'll get into why we're changing it to iodide. It comes from iodine. And iodine is a halogen, and that column is always -1. Now we're starting off with one really, really simple problem here, so we can kind of already figure this out. The idea is these already add up to 0 overall charge. +1 plus -1 equals 0, which means I only need one of each of these, okay? But I'm going to show you the whole cross-drop method, all that, and reduce. What we then do is we'd write out each of their chemical symbols. So we'd write K, and I actually would write in the charge with it, write it as an ion. That's why we practiced that early in like unit 1. Iodine is -1. And essentially the idea would be, I mean, technically we could just combine these and be done, Ki, because they are canceling each other out for overall charge. But if we're going to consistently follow this CDR cross, drop, and reduce, what we do is we cross the 2 charges like that. You see that I'm crossing them to opposite sides to the right-hand side of the symbol. Okay? So that's the cross, and then I drop the charges down. So K, okay, it would be like -1, I, +1. All right? you can say drop is that it drops to the bottom, or you can say drop the charge part of it. So we have K1I1. And then we would reduce this. Well, we can't get anything lower than 1. We can't have decimals in terms of parts of atoms present in the formula. So this is the final formula. The only other thing to recognize, and this is because it comes up in chemical equations when we balance and everything, is we do not write 1. So even though it's K1I1, we wouldn't write that. If we write Ki, I know there's one K present and one I present, and I need to indicate if I need more than that by writing a number, but I don't need to write 1 to reiterate or basically just kind of, really kind of post it that it's 1. We know that it is, so Ki is my final formula. All right, so I know that was a long, slow method, I felt like, for an easy problem, but again, the idea is identify the charges, crisscross those charges, eliminate the positive and negative sign, and then reduce down. We're going to see how some of these, we'll start seeing how we'll get to the reducing and other parts like that. And again, the overall charge has to add up to 0. So barium sulfide, so we're going to take this one a little faster. So barium is an alkaline earth metal, it is +2. And sulfide is in the column under O, which is -2. Okay? So what I have here is I have Ba +2, S -2. I would crisscross those charges, so it looks like, and I'm going to already drop the charge part of it, so plus and minus, and it looks like it's Ba2, S2. This is where the reduce has to come into play. This is not your final answer. All right? This would be incorrect. Because both of these, I can divide 2 into both of these, I reduce it down to the least common least common ratio. It's already a 1-to-1 ratio, so I change this to BAS. Really what you need to think is, can you divide both numbers by 2, or can you divide both numbers by 3? Those are the two most common ones that come up. Okay, I doubt you'll run into, can you divide both of them by 4? If you can already divide them by 2. All right, so can you divide both of them by 2 or 3? But you have to be able to divide both of them. But there you go, BAS. Next, magnesium oxide. Magnesium is in the same group as barium was. Oxide is the same group that sulfur was. So I have Mg +2, O -2, crisscross, I get Mg2O2, and then I reduce that down. I can divide both of them by 2. MgO is your final answer. All right, real quick, this is why my other method where I add them up, +2 and -2, also works, because obviously if I have 1 of magnesium and 1 of oxygen, they already add up to 0, so I already know that's 1-to-1. All right, lithium oxide. Lithium is in group 1, +1. Oxide we just did is -2. You should get pretty used to these charges, so this is something that you might not have to look every single time at the periodic table, but obviously it's there to help. So lithium +1, O -2. This time I crisscross and I see I get Li2O1. This I cannot reduce down. I can divide both of those numbers by 2. I do erase the 1 and I'm done. Whoop, why did that erase? Li2O. There you go. Calcium nitride. Calcium's +2. Nitride is nitrogen. That's going to be our first -3. And I have Ca2. Oops, see, I'm already trying to. Ca +2. Oh my gosh. N -3. Crisscross. Ca3 N2. I can't reduce that. I can't divide both those numbers by 2. I can't divide both those numbers by 3. So there's your final formula. Okay? And this overall comes out to 0 because we're saying I'm multiplying +2 times 3, which would be +6. -3 times 2 is -6. +6 plus -6 is 0. I really want to hammer that point across. Hint, hint, hint. Aluminum phosphide. Aluminum +3. Phosphorus is -3. It's underneath nitrogen. Hopefully you can see what's about to happen here. +3, P -3. I do crisscross. Al3, P3. Hey, they're both 3, so I can divide it by 3. And so my final formula is ALP. All right. So that was name to formula. So what about formula back to name? Okay. So the two things we need to understand here is the metal will always keep its name. So whatever you see, you're just going to write down that metal right off the periodic table. Hopefully you spell it right because you're looking at the periodic table. And then you include the non-metal's name, but you change the ending of the name to "ide," like you saw, okay, with oxide and iodide and stuff like that. So again, there's only so many non-metals up there. You're going to use the same 7 or 8 non-metals over and over again and hopefully get used to their name. So, I mean, this one right here, I'll write a couple of these out. These are going to be a lot faster. This is an ionic formula, metal, non-metal. I write the metal, sodium. And then Cl is chlorine, so I change that to chloride. And that's it. All right? Big thing is no prefixes for ionic compounds. Okay? We just write the metal and then the non-metal with ide. So this one right here, I don't even care about the subscript, okay, or anything like that. I just look at it, I go K, K is potassium, O is oxygen, which becomes oxide. One more, Al2S3, Al is aluminum, S is sulfide. Okay, I don't need to show anything about why there's 2 Als and 3 sulfurs because the charges do that. Okay, so I don't need any prefixes. I don't need to write dialuminum or trisulfide. It's just aluminum, sulfide, metal keeps its name, non-metal changes it to ide. I'm not going to do all this. Would be barium bromide, calcium phosphide, aluminum fluoride, and there we go. All right, now we get to another group. What about multivalent examples? Multivalent, okay? And we'll probably get to one more set here. Yep, definitely. Okay. So multivalent, what the heck does multivalent mean? Multivalent means that that metal, that ion, can actually have multiple different charges to it. Okay. So these are going to be usually the transition metals. That's why we kind of have been avoiding them, is they don't have just one charge, unlike the other columns where we say +1, +2, +3. We're going to see that they could have multiple charges. Sn and Pb are included in this. They are in group 14 under carbon, so be aware of them. They're ones that are, they're tin and lead, so they're also really tough to find because they don't look like tin and lead based on the chemical symbol. This does not include zinc, cadmium, and silver. Okay, one thing to understand, zinc is always +2, cadmium is always +2, and silver is always +1. So because they won't do any other charges, those examples don't need what you're going to see with this Roman numeral in a little bit. Okay, so zinc, cadmium, and Ag are ones we're going to have to be careful of. All right, we're going to use the same process as ionic compounds with the cross-drop reduce method, but then we're going to have a Roman numeral to indicate the charge. Okay, so we got to be understanding of what the Roman numerals are, and we need to know Roman numerals basically up to 7. So I don't think there's a slide for them. Nope. Okay. So 1, 2, 3, 4, 5, 6, 7. Roman numeral 1 is I, 2 is II, 3 is III, 4 is IV, 1 before 5, 5 is V, 6 is VI, and then 7 is VII. Okay. It's too bad we don't really do a lot of Roman numeral stuff anymore, but we get to do it here. So the Roman numeral represents the charge of the metal. So if it has a 1 next to it, that's +1 charge, +2, +3. We do get weird ones, +4, +5, +6, and +7. So we're going to have to watch out for those. Okay? But then once we identify that, we crisscross it, put them down at the bottom, and reduce the charge as needed. So here we go. So manganese 4 phosphide. So that means manganese is +4, Phosphide, the nonmetals you always know the charge of. You look at the periodic table, that's -3. So this would be manganese is Mn plus 4, P minus 3, and I crisscross. And I get Mn3P4. And that's it. Okay? Because this would be plus 12 charge, plus -12. Oops. Funky looking 2. And that equals 0 overall charge. All right, so here's already a tricky one. Silver oxide. Silver oxide. So this is one you're going to have to remember. Silver is always plus 1. Okay? You're going to have to remember that one. Oxide is -2. So this would be Ag plus 1, O minus 2, crisscross, Ag2O. Copper 2 sulfide. This is, and we actually say that. Okay, so copper II, we actually just say out loud what the Roman numeral is. Copper 2 sulfide. So this means copper's plus 2, sulfide's minus 2. So Cu plus 2, S minus 2, crisscross, Cu2S2, reduce it down, Cus. I can divide both of them by 2. Cobalt 2 fluoride. Cobalt's plus 2, fluoride's minus 1. Cobalt plus 2, F minus 1. Oops, there we go. Crisscross, CO1F2. Get rid of that 1. COF2. Zinc nitride. Zinc's your other mean one. Zinc we have to remember is plus 2. Nitride's minus 3. So zinc plus 2, N minus 3. Zn3, N2. Can't reduce it. I'm going to skip that last one. I mean, it should have just been TiO, titanium 2 oxide. All right. What about if I give you a formula that has one of these multivalent ions, and you need to write the formula for it? All right. So, what we need to do here, I'm not going to use this whole T-chart thing, okay, is you do still write the metal's name, and the nonmetal will still end in "ide." So you treat it just like any other ionic compound. But we do need to figure out the charge, okay? And this is where we have to remember the overall charge of the compound has to come out to 0. So we do have to play around and figure out the charge. So it's best just to jump into this. So I have H, oops. Come on, thing. HgBr2. Okay? And maybe it's what T charge is something like this, which is fine. Okay? What we do is we know what the charge of the nonmetal always is. And Br has a charge of -1. Okay? So this is -1, but there's how many of them? 2. So there's an overall charge of -2 on the nonmetal side. On the metallic side, Hg, which is mercury, I only have 1. Okay, there's only 1 mercury here, so it has to have all the charge to cancel this out. Like when I add up the left and the right side, it has to equal 0. So this is going to be plus 2. And now that I know it's plus 2, that's the Roman numeral. So this would be mercury 2 bromide. I figured out the Roman numeral. I could have written mercury bromide right away. All right. Now the thing is, we're only doing this if it's a transition metal or tin or lead. If it's something like we just did, we're not writing Roman numerals because they never have any other different charges. Mercury can actually be plus 1. It could be plus 2 as well. So that's why we need to identify it very, very clearly. And I did that by figuring out the charge of the nonmetal. So this one right here, PbS2, good example here, PbS2. Okay, S is -2. I have how many of them? 2, based on the subscript. So the total charge is -4. PB, I only have one of them right here. So it needs to cancel out that -4 and be +4. If I add those up, it equals 0. So there we go. The charge of this PB, which is lead, is going to be 4. So this would be lead IV, in parentheses, we do write this in parentheses if you haven't noticed, sulfide. All right. Of course, they give you a mean one. So cadmium fluoride. Okay, well, CdF2. This is one of the ones that is not multivalent, so we treat it just like the other ones we've done. So we just write the name, cadmium fluoride. So that one you got to watch out for. That's all I can tell you. Cadmium, silver, and zinc. All right. SnO2, Sn, oh, not O2, O. This one's pretty easy. O has a -2 charge. There's only one there, so Sn must be +2. There's your Roman numeral, tin 2 oxide. All right, there we go. We needed one where we actually get a little bit tougher with it. So Fe3P2. All right, P has a -3 charge times 2 has an overall charge of -6. On the left-hand side, I need this to be +6 to cancel it out, right? But this is finally an example where there's 3 atoms. There's 3 irons, and these are going to add up to +6. So I need to now go backwards, and just like I multiplied going down, going up, I got to divide this by the subscript. Divide by 3, it's going to be +2. +2 times 3 irons is +6. So be very careful of that. We have technically been doing that, but we've only been dividing by 1. Okay? So we do figure out the overall charge on the nonmetal side, but then have to divide that by the subscript on the other side to get the actual charge of the atom. So this would be iron 2 phosphide. Now, I will say real quick, some people sit there and go, can we just do the reverse crisscross? And go, hey, that's going to be +2. You don't know whether this got reduced. That's the biggest thing. You don't know whether it got reduced down. So you could try it, and you could get lucky and be correct, but you don't know for sure if you're just doing a reverse crisscross. So I do have people ask me that. Okay? Are there examples where it works? Sure. But it's not going to work if it's something that got reduced. All right, last group are ternary ionic compounds. Ternary compound, as we talked about last unit, is where you have a compound with 3 different elements. This means you have a polyatomic. Okay? If you have a polyatomic, all right, sorry, you have a polyatomic ion. Remember, a polyatomic ion is an ion that has 2 or more atoms in it that has an overall charge. Okay? This can be cations or anions. We will give you these. We will give you what they look like, and we will give you the name of them. All right? So you just need to be able to use it. All right? So here's a bunch of examples of them, as you can see. All right? Where you have 3 elements in it. Okay? Now, the writing of these, we follow what everything else has done. The writing, the name of them or whatever, the polyatomic ion just keeps its name. So you don't have to do anything special. It just keeps its name. You just got to pay attention. Do you need to have a Roman numeral with the metal? Like, polyatomics almost never, they don't have metals. They all have, I shouldn't say that. There are a couple that have a metal in them, but they almost all are anions, so it's going to be a metal and a polyatomic. There's only one positively charged polyatomic ion, and that's ammonium. Okay. So here we go. So potassium sulfite. So we follow the same rules. We go potassium is +1. Sulfite. Now, polyatomics end with ite or ate. That's your other clue when you have a polyatomic ion, is they end with ite or ate. All right? So this is not sulfide. What you'd have to do is you'd have to go on your polyatomic sheet, and you would see that this is SO3 - 2. So you now know that this has a -2 charge. We then can do our crisscross method, SO3 minus 2. We do crisscross to the outside, and we get K2 SO3, yes, 1, but we don't need to have that 1. Okay? But we do need to make sure that we keep the polyatomic as a single unit. This is how this is what sulfite always looks like. You cannot never, ever, 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 ever mess with the subscript of a polyatomic ion. Okay? Keep that there. Magnesium hydroxide. So magnesium is +2. I mean, this is immediately making me a liar. Hydroxide is one of the two polyatomics that don't end with ate or ite. And so this is not hydrogen. This is OH minus. So this is -1. So I have Mg +2 and OH minus. So I do crisscross these, and then you're going to see what happens. So this would be Mg1, so I don't write it, and then OH2. But the idea is I need 2 OHs. I need 2 of these. So I put it in parentheses, and I put the subscript on the outside of it. Okay? So make sure you recognize that we use parentheses to protect the polyatomic ion. And then if I need to have additional ones, I write the subscript on the outside of those parentheses. A couple more examples. Aluminum acetate. Aluminum's +3. Acetate is C2H3O2 minus. So -1. I'm going to crisscross these, +3, C2H3O2 minus, crisscross, Al1. And then since I'm going to need multiples, I'm going to protect this. C2H3O2, 3 on the outside. One more. Iron 3 phosphate. Iron 3 phosphate. So iron 3, that means it's +3. Phosphate is PO4 -3. I'm going to crisscross those. Fe +3, PO4 -3. Crisscross, I get Fe3, PO4 parentheses 3. But I can reduce that, so I divide both by 3. And I get FePO4 is my final answer. All right. How do I write the name? Pretty straightforward. If you're going from formula to name, you write the cation, the metal. Again, if it needs a Roman numeral, use it. Polyatomic, you just copy it straight onto the paper. So polyatomic, we don't do anything but copy it. So right here, you have lithium and then Cn. So this would just be lithium cyanide. This one, Sn is tin phosphate. So I write tin phosphate, but tin is a multivalent one. So I do need to do this one for a moment. Okay. So SN3PO4 2. So what I do here, PO4 is -3. You get that from your polyatomic sheet, times 2 is -6. That means this has to be +6, but I have to go back up. I'm dividing it by the subscript. So this is +2, so tin 2 phosphate. One more example. Another one with, so this would be chromium nitrate. And I'm going to do it up here. Nitrate's -1 times 3 is -3. This side has to then be +3. There's only 1 there, so I'm dividing by 1. So this would be, squeeze it in there, chromium 3 nitrate. And that is it. Okay? So there's plenty more of good examples that you can work through. Obviously, you have a lot of practice to be doing, but then we are all finished. Thank you.